Hello and welcome. My name is Gianni Allevato, and the topic of this presentation is an embedded air-coupled ultrasonic 3D sonar system with GPU acceleration. First, let's take a look at upcoming robotic applications. Robots will start delivering us packages, they will support our elders, and they will also help us in the office. Besides that, they will be used in industrial applications, for example for mining, and also for rescue operations. All these examples show that robots must navigate safely in very different and challenging environments. Therefore, it is important that robots are equipped with different types of sensor systems to monitor their environment. These systems must be different, such that their strengths and weaknesses complement each other. For example, camera and lidar systems have difficulties when it comes to transparent and reflective surfaces. In contrast, ultrasonic sensors are not affected by the optical properties of a material, therefore they operate robust when it comes to these conditions. So let's take a closer look at ultrasonic sensors. Typically they are used as one-dimensional rangefinders, and they are arranged on a so-called sonar ring surrounding the vehicle for a full 360 view. The problem of this arrangement is that there is no height differentiation, so the robot can tell whether a detected object is a real obstacle or not, like in this case. The second problem is that the angular resolution is really limited, so the sensor doesn't know that there are two obstacles, and it doesn't know in which direction these obstacles are located at. Therefore, the robot can't find a valid path in between those obstacles. However, there are already advanced sonar systems which can detect range and direction. For example, by the research group of Robin Kerstens and Jan Steckel, they created a sonar system based on a broadband ultrasonic transducer for illuminating the scene, and an array of 32 MEMS microphones for receiving the echoes. And by using beamforming, they can not only detect range, but also direction to generate images like here. Our research group previously focused on a MIMO array, which uses not only one transducer, but rather 64 of them, and we used the Murata MR40S4S transducer, which is a narrowband 40 kHz resonance transducer. We insert this type of transducer into an acoustic waveguide, and this way we can create unambiguous images like we see here. In the scene we can clearly detect those two spheres in our horizontal B-scan. A new type of array we created doesn't use a waveguide, but a spiral arrangement instead. In this way we can also create high resolution images like this here. However, for implementing such a sonar system into a mobile robot, such a system should be cost-effective, compact, self-contained, and should still provide high frame rates. And these requirements are not fulfilled by this type of array, as it is rather large and uses a lot of components and electronics. This is more aimed at industrial applications. Therefore, we decided to create a new type of array which uses only one transducer and an array of 36 MEMS microphones. And these are arranged on a triangular grid with half wavelength spacing. And this sonar head is designed to be modular, so this is a 4-layer PCB stack, and each PCB has a certain task and is interchangeable. The first PCB is the microphone PCB, which has 36 Knowles microphones. These are small scale, these are broadband, and they already provide a digital output signal as pulse density modulated signals. The next PCB is the transducer driver PCB, and here we generate the burst signal digitally by using a digital output pin, and this digital signal will get amplified by our driver. And since our transducer is narrowband, this will get converted to a sine wave, like this. And as you can see, our driving signal is digitally created. Our microphone signals are already digital, so our full front end is almost purely digital, which allows us to have very few components, and in addition, these components are not expensive at all. So next comes the FPGA PCB, which is the heart of our Sonar head, and we use an Intel Max 10. This creates the burst signal, and the FPGA will also be used for receiving the microphone data and converting them to pulse code modulated signals, like we see here. And for this we use a Sync 3 kick filter, but we don't use only one of them, but rather 36 of them to convert all microphone signals in parallel. The last task is to provide a communication interface for transferring the data to our communication chips, which are positioned on the last PCB. We have two versions of this last PCB. One features a high-speed USB FTDI chip, and this provides high data transfer rates of 480 Mbit per second to our main signal processor. As an alternative, we have a Wi-Fi microcontroller PCB based on an ESP32 Rover B module, which can be seen here. And this way we can achieve up to 14 Mbit per second of data transfer rate, and this is wireless data transfer rates. And these are connected to our main signal processor, which is an Nvidia Jetson Nano single board computer. This features a CPU, but more importantly a GPU, which allows parallel signal processing. For this we created a custom C++ program, which is based on CUDA for signal processing and OpenGL for parallelized visualization rendering. So let's take a closer look at our parallel signal processing. Here are our received 36 microphone signals. The first step is to convert them into the frequency domain using fast Fourier transform, and we use the parallel FFT library from CUDA, which is QFFT, and this will then be transformed in parallel. But we don't create a full spectrum, but only the first non-redundant half of the spectrum, and this automatically generates the analytic spectra for these signals. Next, we multiply these spectra with the frequency response of a matched filter to improve SNR, like this. And now comes the computational intensive part, which is the conventional beamforming. Basically, conventional beamforming is a matrix multiplication. And this matrix here is the spectra matrix, which we also see here. And we multiply this matrix with a beamformer matrix, and this converts the 36 microphone spectra to K spatially filtered spectra of a given number of scanning directions. And you can imagine when we increase the number of directions to be scanned, this matrix multiplication can become very large. So it is important that this multiplication is implemented very efficiently. And we have done this by using parallel tiled matrix multiplication for parallelization. And we also evaluate only the frequency bins, which contain a good amount of signal spectrum, and this really shrinks down the number of multiplications to be done. Okay, the next step is to convert the spatially filtered spectra back to the time domain using the inverse fast Fourier transform, also provided by QFFT. And here we obtain K spatially filtered signals. The next step is to extract the envelope, and we do this by forming the absolute value of each element. And these signals will get color coded and then used for our imaging. Okay, now I could show you some measurement results from the lab, but you can also find them in the paper. So instead, I want to show you some real-life situations and the performance of our sonar system. So my colleague Matthias Rutsch created this video setup consisting of a camera and the sonar. And now we will take a look at some real-life situations. First, we check out the two-dimensional horizontal scan, and the amplitude is here color-coded, so the obstacles will appear as yellow dots. And you can see that we can not only detect range, but also direction of these obstacles. And also the frame rates are sufficient as we move along, so we can really track down the obstacles appearing. Next comes the 3D scan, and this time the range is color-coded. So as I move my hand closer to the camera, it gets more yellowish. And we can also detect two obstacles in the same range. Okay, and now to conclude and to give an outlook, we have seen a very efficient and viable implementation of advanced sonar system, which makes use of parallel signal processing based on CUDA, and this really speeds up the image formation. We have seen that this type of sonar system is capable of finding range and direction of obstacles, and of course we want to implement this into a mobile robot like we see here. So we want to evaluate the sensor fusion of the sonar, a lidar and the camera, and this has been a master thesis by Hinrichs. In addition, we want to take a look into automated object counting and localization, and we want to extract the velocity of objects by using the Doppler effect. Okay, then I can say thank you. Feel free to ask questions in the question session, and stay safe. Goodbye.